Are all of you ready for today's lecture? In the course of human events, there come threats so vile, so horrible, that none of you can withstand them. We need a superposition. Huh? Oh, I came up with it on the spot. Yeah, I stood up and I'm like, I should start my lecture with my hands on my hips. And then it just kind of went from there. Welcome to my mind. We're going to be talking about superposition. Do any of you know what superposition is? That's actually understandable. This is one of the more high cognition pieces of here. Superposition is only used when a certain problem is encountered. Okay. Now we talked about what's the difference between using a Thevenin equivalent circuit and an equivalent resistance circuit. When would we need one over the other? When would we ever need a Thevenin equivalent circuit?
I mean, if you're going to use it multiple times, you don't have to keep solving the equivalent circuit.
So the idea here is, as I produce to you, if you have a circuit and you want to plug stuff into it, but that circuit already has a voltage source, then you're going to be creating a Thevenin equivalent circuit. Right? So it just allows you to easier calculate when there's a voltage source present, but not all of that voltage goes to the load. Okay? An equivalent resistance here, anytime you do equivalent resistance, the circuit can't have a source. There cannot be a source. Okay? A voltage source or a current source. I should just say power source here, because it could be either. And here, there's no power source. But what we haven't talked really about is what happens when there's two power sources. That's when superposition is necessary. Okay. So here, you can use superposition to create a Thevenin equivalent circuit. Okay? Okay, but you can't, it doesn't go backwards. This is a tool that only is necessary when you have multiple power sources, and it allows you to figure out what the voltage on a component is, okay? So really the best way to explain this is to give an example. Now, I'm gonna be frank with you here. We have done labs in the past where we tried to use superposition in a lab setting. It didn't work. In fact, we got way wrong answers. I don't know what's wrong with it, but we couldn't make it happen. So I don't really know how valid this is. There are a whole bunch of conditions that the textbook places on when you can use superposition. It has to be linear components. It has to be very specific resistance-only circuits. All of that. When I actually measured it, we couldn't make it happen. And then that's kind of disappointing to me. So I'm not really going to be teaching you a whole lot about this. And I'm not going to be expecting you to do any problems over this. Okay? just because I don't like superposition in a lab setting. If it doesn't work, it's trash to me. Like, you can't recreate it in a lab. There's something wrong. But the idea here is this. Okay, I've got a voltage source. I've got a current source. And we'll go ahead and ground this. Okay? I now have two sources inside of the same circuit. If I have R1, R2, R3, let's say these are all 100 ohms, we'll say Vs is equal to, I don't know, 10 volts. We'll say Is is equal to, I don't know, 0.01 amps. Nah, we'll change this. 0.1. There we go. Okay, the question is, how do we solve this circuit? Okay. Now, according to the principles of superposition, the first thing that we have to do is analyze one source at a time, okay? But then the question becomes, all right, so I hide this one. How do I calculate this branch? Over here, what does it mean? Well, we have to take our understanding of open circuits and short circuits and apply that now to how we treat multiple voltage sources, okay? Here, if we just simply treated this as if it was a short circuit, what does that mean? Well, it would mean that we're assuming that there's no voltage put across this piece by the current source, right? That would make sense. The current source probably isn't going to be applying any voltage across there. But on the flip end of that, it also means that the current source is probably going to preferentially send current that direction. If we had a resistor here, a resistor here, we just shorted that, it might preferentially want to send current through a voltage source, which probably isn't real either. What we end up doing to treat these sources as is we say a voltage source is going to be treated like an open circuit. Actually, let me check and make sure that that's true. Man, I hate superposition. I think that's right. Oh no, I am actually wrong. We treat a voltage source as a short circuit. Okay, and then we treat a current source as an open circuit. Okay, the idea here is that yes, this can send current through there, but it probably won't change the voltage. In fact, it won't change the voltage. So if we treat this as if it's a short circuit, we're going to assume that there's no voltage being applied across those terminals. The voltage is being applied by a voltage source. On the flip end of that, if we treat this as an open circuit, we're going to assume that it's not going to force current through there, because it won't. You're not going to have an additional current being shoved through a current source. So we treat voltage sources as if they're shorted, and we treat current sources as if they're open. Okay? And I'll detail that to you as we solve this problem. Yeah?
So for this scenario, do we assume that both the sources have no internal resistance?
We're going to assume so, yes. If they did have internal resistance, they actually become dependent sources. And dependent sources don't apply to superposition because then you actually have to plug them into a calculation and assume that they're not an independent source. This is only for independent sources. Yes. Like here, if I tried to shove current through a real life source, there is a small amount of dependency in how it would change the output, which is why I hate the superposition principle. Okay, if you had like AA batteries, those are almost impossible to shove current through. It actually causes them to explode. They might actually work in this type of situation. But in any case, it's very unlikely you're ever really going to be working in a case where you have multiple sources present. So superposition principle is something we teach you, and then you never use again. All right, okay, so we basically have to solve this circuit twice and then sum the components, okay? So I'm going to solve it once. Well, I'm going to solve it both times over here because it just works better for the live stream. All right, which one do we want to tackle first? The voltage source or the current source? All right, we'll start with the voltage source. So here, I'm going to redraw this circuit, and every voltage source that isn't this one, I'm going to treat as if it's a short circuit, and every current source that isn't this one, I'm going to treat as an open circuit. Okay, so here I have 3 resistors. Oop. There we go. Okay, so again, we're replacing our current source with an open circuit, which is great. We have R1, R2, R3. We can solve this system. Now, before anything, what is VR2? Why is it 0? VR2 is 0 because we can't have any current that flows through it. Because we can't have any current that flows through a resistor, we cannot have a voltage in that component. It's only true for resistors, but if there is no current, there is no voltage. Which means all of this voltage, there's only one loop. We can basically ignore the right half of this system. Okay, we know both of these are 100. I'm going to tell you right now, since these are equal, VR1 is equal to 50. Oh no! 5 volts. VR2 is equal to, VR3 is equal to 5 volts. The end. Okay? Anybody want to go through how I solved that? Can you figure it out yourself? No, Seth says no. You want me to go through it? Oh. Okay, I was going to say all of you are... I'm just burning through this because this is kind of old hat at this point. What is a resistance? Can we go back to class 1? All right, so this is the first system. Our second system, what we're going to do is we're going to treat the voltage source as if it was a short circuit. So we'll go ahead and take this. Okay, and then here, all of the current is going to go through here, which means all of this current, which is 0.1 amp, is going to go through this, which means VR2 is equal to 10 volts. Half of the current is going to go to each, which means VR3 is equal to 5 volts. And then VR1 is equal to 5 volts. And then it all goes back into the end of the current source. Okay? Any questions on that? Anybody want me to solve that?
Wait, you just, how do you find the total voltage?
You should just be equal to IR.
Yeah. Well, in here I then use the current division principle. Current division principle says both of these are equal. Both of them are going to have the same voltage, but both of them are also going to have the same current. So the current plus this one has to be equal to this one. So since both of those currents have to equal, and because both of the resistances are equal, they're going to have the same voltage. Well, they have to have the same voltage because they're in parallel, but they're also going to have the same current. You're getting ahead of me. Do you want to come up here and explain that? Or do you want me to finish? You're right. You are right. You're just like 2 minutes ahead of me. So what I'm doing right now is I'm now labeling pluses and minuses. Why is that important? You'll see. Here this is plus, this is minus. Here this is plus, this is minus. This is a positive 5 volts in this direction. This is a positive 5 volts in this direction. When we do the superposition principle and we sum them, we're adding 5 volts in this direction plus 5 volts in this direction. The total voltage on R1 is 0. Huh?
Stalemate.
It is a stalemate. Now, additionally, along with that, because this is a 0 volts, there is no current flowing through this component. No voltage, no current. Fascinating. This has 10 volts going this way. This has 5 volts going this way. This has 5 volts going this way. This is 0 volts, so it doesn't really matter. So this becomes 10 volts across this component. This becomes 10 volts across this component. You were right. There's no voltage at R1. But that's why. Superposition is friggin' weird. Any questions? By the way, this is only 0 because of the way that I set this up. Had this been 0.05 amps, there would have been a voltage at R1, but it might have been negative. Okay? So it's just the way that I set up the sources. You play around with